Okay, so now we are starting the session. So welcome everyone in the problem solving session for week 6 for the course Traffic Engineering. My name is Tanu Singh. I am a PMRF scholar at Department of Civil Engineering, IIT Kanpur. So in this session, firstly we will summarize week 6 lecture. Then we will discuss some of the practice questions and also try to resolve all your doubts. So starting with the session. So today we will be discussing the intersection control and critical aspects of operations. So first let us understand what is intersection. So an intersection is a location where two or more road meets, crosses, merge or diverge. Now why are intersections so important? Because they are the most critical elements in a road network. Even if a road section are operating smoothly, intersection often become as bottlenecks. Vehicles are coming from different direction, going to different directions, so naturally traffic conflict occurs. Then another major aspect is the safety. So since a large number of vehicles, there is a high chance are traversing over the intersection, so there are high chances of the accident intersection. So not only vehicles but also the pedestrians and cyclists use the intersections heavily. So as a traffic engineer, our objectives are firstly to ensure smooth traffic flow within the available capacity, and second was to enhance safety for all road users including vehicles user and as well as pedestrians. At any moment if my screen is not visible or I am not audible, please let me know. So now coming to the conflict points at intersections. So conflict points are locations where traffic movement intersect in some or the other way, like for example they may merge, they may diverge, they may cross or they may weave. So we classify conflicts in two categories. One is major conflicts, the other one is the minor conflicts. So the major conflict is mainly includes crossing and weaving. These are more dangerous, whereas minor conflicts includes merging and diverging. These are comparatively less severe. So now understanding the four-leg intersection where all turning movements are allowed. So here the conflicts that can occur. For example, this is the intersection, four-legged intersection. Vehicles are coming from this direction and they might go this direction, they might go right or they might go straight. Similarly, these three movement for all the three legs. So these green dot represents the diverging when the straight moving vehicle diverges from the left moving. So there is a movement of moving left or moving right. So there is a movement of diverging. For all the roads, therefore, and the yellow represents the merging when, for example, vehicle traversing from this direction merges on the left direction. So there this here occurs a merging conflict. Similarly, a vehicle traveling from this direction takes a right turn and comes to this this road. So there here it merges. So yellow represents the merging, whereas the green represents the diverging conflicts, and red represents all the crossing conflicts that occurs in the four-leg intersections. So total if we count the number of crossing, merging and diverging, so number of crossing conflicts will be 16, whereas the merging conflicts are 8, whereas the diverging conflicts are also 8, 2 from each directions. So therefore, the total number of conflicts that occurs in the four-legged intersection is 32. Uh, okay. And now coming to the three-leg T intersection. So this was all about the four-way intersection, and three-way intersection will have total 9 conflict points. As you can see in the figure, these diverging, this is diverging, whereas this is merging. These three are the crossing. So if we count all of these points where merging, diverging and the crossing conflicts occur, so for three-way it is a 9 conflict intersections. So so you can clearly see means more conflict points means higher probability of crashes. And remember, when pedestrians are present, additional vehicle and pedestrian conflicts are also added to these. So it is very important to reduce these conflicting points when we design an intersection. Now coming to the factors affecting safety at intersections. So now the questions comes in, like what determines whether drivers can avoid these conflicts. So there are two major factors. First is visibility. A driver must be able to see a conflicting vehicle or pedestrian in sufficient time. If a driver cannot see properly due to obstruction or poor sight, the chance of collision increases. Second is the availability of the safe gap. Suppose a vehicle wants to turn right. So let's consider that this is the minor road, and the vehicle wants to turn right from a minor road. So this is the minor road, and vehicle wants to turn right to the major road. If a traffic volume on the major road, if the traffic volume on this major road is very high, so what happens there? So there may not be a sufficient gap for this vehicle to turn right. So this creates an delay and sometimes a risky behavior. Therefore, intersection design aims to firstly reduce the number of conflicts, second reduce the severity of the conflicts, and also convert major conflicts into minor ones whenever it's possible. So after this, now coming to the level of intersection control. So there are different levels of intersection control. We classify them into three. We classify them into three levels. First one is passive, whereas the second one is the semi-control, and third one is the active control. So for passive control, there are no signals, no stop signs, no yield signs. Driver follow basic traffic rules such as giving priority to vehicles already intersection or to vehicles approaching from the right. So this is only suitable when there is low volume intersection with good visibility. Second is semi-control. So here we assign a right of way explicitly using the stop and yield signs. We may also use channelization or roundabouts to guide movements. Third one is the active control. So this includes traffic signals or grade separations like flyovers. So traffic signals separate movements by time. Conflicting vehicles move at different time. So in traffic signals, what do we divide the use of this area with respect to the time, uh, so that different vehicles, so the conflicting vehicles move at different times at this particular area. Then the grade separation separate movements by height. So different levels eliminates conflicts entirely. So so we do not we should keep in mind that we do not immediately go for the this highest level. Firstly, we upgrade control only when lower levels are insufficient. Firstly, we try with the signs or channelization, or we do with the roundabouts. But if still it is not we are not able to control the number of conflicts, we further increase the level. Okay. Now starting each level one by one. So first level was the passive control. So here there was no explicit right of way assignment. Mainly the operation is only governed based on the rules of the road. No stop, yield sign or traffic signals. They are mainly applicable when the intersection is a low volume. There are minor intersections and locations where adequate side distance is present. Then the right of way rules, like vehicle must yield to traffic already in the intersection. When two vehicles arrive simultaneously, driver on the left yields to the vehicles on the right. And the key requirement is adequate side triangle and availability of stopping side distance. So coming to the as mentioned, the requirement is there should be an adequate side triangle and the availability of stopping side distance. So here the side triangle concept means if a vehicle is present here, he is able to see the vehicle coming from this leg of intersections, so that it has a sufficient time for its perception and to stop a vehicle before a conflict that can take place. So drivers must see each other in time to stop safely. This is mainly based upon the stopping side distance, which is calculated using the formula 0.278 Pt plus V square divided by 254 F plus 0.01 G, where V is the speed of this particular vehicle, whereas the T is the reaction time, the time required by the driver to react or to apply the brakes is its reaction time. F is the friction of the road, and G is the grade. If the side distance is inadequate, for example, if there is a building situated at this position, so there is an inadequate side distance. So on that cases, we install the stop or yield signs, or reduce the speed of vehicles, or we try to remove physical obstructions if we can, like walls, shops or structure near the corner. So so if there is an adequate side distance, then it can significantly improve the intersection safety. Now coming to the level 2, that is semi-control at intersection. Semi-control is this level is mainly used when passive control is no longer adequate. For example, if side distance is poor, if frequent crashes are occurring, or if traffic demand has increased significantly, we cannot just depend upon the basic right of way rules. So on that cases, we apply the semi-control system. So semi-control, these mainly uses the stop and yield sign. So this type of control is used when a minor road enters meets a major road. The traffic on the major road gets priority. It is also used when driver compliance with basic rule is low, or when an unsignalized intersection exists with a signalized corridor. For example, if this is as is intersection, for example, and further here is another intersection, and if we assume this intersection is signalized whereas this intersection is not signalized, so in this intersection we try to use the control, that is semi control, using the stop or yield sign. For example, if the traffic light is green in this case and vehicle are driving, at that moment we can use the stop sign for this minor road, whereas when the traffic light is red for this intersection, on that cases we can use yield sign for the vehicles entering the major road. So these are this was about the semi control thing. Then coming to the yield sign and stop sign. So under the yield sign, the driver must slow down to a reasonable speed. Stopping is not mandatory if a safe gap is available. The driver can proceed without stopping. However, if gap is insufficient, the driver must stop and wait. So this type of control is used where traffic conditions do not require a full stop every time. It is commonly used at generalized turn lanes. On the other hand, the stop signs. So stop signs are generally used when the major road traffic volume exceeds about 6,000 vehicles per day, where sight distance is restricted, or where crash history indicates safety problem. So yield means conditional stopping, or we can, and stop means the, or you can say stopping means the compulsory stopping. So now coming to the channelization and roundabouts. So even under the semi control, safety can further be improved through, as mentioned, through channelization or using the roundabouts. So channelization means separating traffic movements into a definite path using the traffic island or the pavement marking. So if an intersection area is wide or open, driver may choose different paths for the same maneuver. So this creates confusion and increase the chance of conflicts. So by using the channelization, we guide the vehicles into specific trajectories. So this reduces the confusion, controls merging and diverging angles, which was different previously, but now it is being channelized into specific pattern. Then it also improves the overall safety. It also helps in providing right turn storage lanes so that turning vehicles do not disturb through traffic. So a special form of channelized intersection is roundabouts. So in a roundabout, traffic moves clockwise. The key rule is that entering vehicle must yield to the circulating traffic. By converting direct crossing conflict into the merging conflict, roundabout significantly reduce the severity of crashes. So this was about the level 2 semi-control at intersection. Now coming to level 3, that is mainly being controlled by the traffic signal. So when semi-control is not sufficient, we move to level 3, that is traffic signal control. So this is required when intersection volume are very high and bottlenecks are observed, repeated crash occurs, or when the minor road does not get adequate gaps to enter to the major road. And then traffic signal operates on the principle of time segregation. Conflicting movements are separated by time. When one movement is allowed, the conflicting movement is stopped. As we have seen, there were different conflicting movements. So here the main purpose is to separate the two conflicting movement. Then signal control, both vehicular and pedestrian movements are being controlled by using the traffic signal control. So there are advantages, that is the improved safety, then orderly movement of both vehicles and pedestrians, better coordination in the corridor, and it provides the control of pedestrian crossing. So now coming to the disadvantages. So they introduce delay because movements are not allowed simultaneously, as it was in the case of roundabouts. They may be a signal violation, sometimes rear end collisions increases. Driver may even divert to alternative routes to avoid signals. So these are the disadvantages of the signal control. Now coming to the grade separation, if traffic signal also fails to provide the acceptable performance or reducing the number of conflicts, we use the highest level of control, that is grade separation. So in grade separation, conflicting movements are separated vertically. So that means one movement passes over or under another. This eliminates the at grade conflicts completely. So here these the movements are separated vertically. All the conflicting merging and weaving, all the different types of conflicts is being separated vertically. So this provides the highest capacity and safety, since there are different roads for each of the each type of the movement. So this increases the capacity of the road infrastructure and also increases its safety. However, it is expensive and requires a large land area. Therefore, grade separation must be properly justified. It is typically used on access controlled highways, location with very high traffic demand, or intersection with serious crash history. So it is always stepwise improvement. We do not directly jump to the grade separation. If we are at the first level, we try to increase the safety using from level 1 to level 2, and if still it is not able to justify, we go from level 2 to level 3. We do not try to jump directly to the grade separation control system at intersection. Okay. Now coming to the data for traffic signal justification. So before installing a traffic signal, we must conduct a detailed engineering study. So we need 12-hour for that we need a 12-hour traffic volume count data. We need peak hour classified counts at 15-minute intervals. Then pedestrian volumes count are important. Then delay, study of the delay, queue and then speed data posted in 85th percentile. We also need the condition diagram showing geometric features, crash history with collision diagrams. Then we also need the information regarding the nearby infrastructure such as schools or activity centers. So these are all the data and study required before installing a traffic signal and doing the engineering study. So this signal installation is checked using warrants from the Manual of Uniform Traffic Control Devices. It's all known as MUTCD. However, satisfying a warrant does not automatically means we must install a signal. So there is an engineering judgment is important. Then final decision is it must ensure its improvement in safety and operational efficiency. So I hope I am audible and my screen was visible, and please let me know if there is any doubt till here.
Yes, ma'am, visible.
Okay. Okay, sure. continuing if there is no doubt. So what was this signal warrants that I mentioned just now? So this manual of uniform traffic control devices has different warrants, and we install the signal based upon these warrants. So starting with these warrants one by one. So firstly, the traffic signals are justified based upon these warrants. So mainly the focus area includes the traffic volume and delay, then pedestrian activity, then the what are the school crossing safety during the school hours, then what is the coordinated signals information, if there are any platoon movement along the corridors or not. So evaluation varies depending upon the time period. We also have the 8-hour vehicle volume, then 4-hour vehicle volume, then peak hour factor, then also the pedestrian and school periods. So,
hello, ma'am.
yes.
Ma'am, may I know what is the purpose of this? I want to know whether these warrants means collection of data based on which we can devise a traffic signal. Am I right?
Yes. We will go one by one about all the warrants. Like there are total 8 to 9 warrants. Depending upon these warrants, we decide whether we should install
Warrant
a
means
traffic.
it's a data set data. Am I right?
Yes.
Okay.
These data includes these things. The traffic will, like first will include the traffic volume, the second maybe include pedestrians. So these are the different data I can say. Yes. So now starting with the first warrant, that is 8-hour vehicle volume. So warrant 1 deals with this 8-hour vehicle volume, typically the total workday traffic we can say, because 8-hour is the total workday traffic. Then for this there are two conditions. Firstly, overall vehicle volume threshold, that includes both the major and minor streets data, whereas condition B is the minor streets that suffers excessively because of the delay that it may have due to insufficient gap present in the major street. So this table is being present, that is being used to decide whether it follows the condition A or condition B. For condition A, if the speed is greater than 40 mph, or if the community is less than 10,000, then there is a special condition is that is B and D, that is combination threshold at 80 degrees, 80% of A or C, whether neither A nor B alone satisfies. So depending upon the traffic 8-hour traffic volume, the warrant A is being decided, whether vehicles are what is the percentage of vehicle present on the major street, whereas the vehicle per hour or on higher volume minor street. And depending upon this, depending on what is the number of lanes, we determine if it is greater than what the values present on the table. So this ensures that so we say that the warrant 1 has been satisfied for the has been used as the justification for the signal, installing the traffic signal. If similarly this is for the condition B, interruption of the continuous traffic. So this ensures that the minor street traffic gets adequate opportunities to cross even with heavy major street flow. Now coming to warrant 2, that uses the 4-hour vehicle volume. that is usually morning or evening rush hours. These measures major versus minor street volumes over 4 hours. These are graphically we evaluate the this is the threshold line for different. If there is lane 1 in both the direction, if there is 2 or more lane in one and other has the 1 lane, whereas 2 or more lanes in both the major and minor street. If the 4-hour volumes comes above these lines, then we say that these condition is been satisfied. And there is one special condition, that is 70% of threshold if speed is greater than 40 mph or isolated community, that is the population is less than 10,000. So this warrant mainly captures short-term congestion that may not appear in that 8-hour total volume condition. Now coming to the warrant 3. Warrant 3 evaluates the peak hour traffic volume. This is often near industrial or office complex. The two ways to justify this is, firstly is the volume warrant, that is similar to the warrant 2, and second one is the multiple conditions for the 4 consecutive 15-minute period. Firstly, if the stop time delay is greater than 4 hours for one lane, or it is greater than 5 hours for 2 lane. Second condition is minor street volume is been greater than 100 vehicles per hour in one lane or 150 vehicles per hour in the 2 lane, or the total intersection volume is 650 vehicles per hour in 3 approaches or 800 vehicles per hour in the 4 approaches. And special scenario means adjust the threshold depending upon what is the speed and the isolated communities. So warrant 3 also have this threshold line depending upon what is the number of lanes present in both minor and the major street, and if it is above the threshold line, so this justifies the condition for warrant 3. This warrant mainly helps us to search the number of vehicles mainly present at the workplaces such as offices or the industry areas. Now coming to the warrant 4. Warrant 4 deals with the pedestrian demand. So warrant 4 looks at the number of pedestrian crossing relative to the major street traffic. So here 2 periods has been taken. First is the 4-hour period and second is the peak hour volume, peak hour pedestrian volume. Here the threshold adjustment is done for 70% of the normal if speed is greater than 35 and isolated community is less than 10,000. So here even moderate vehicle traffic may justify a signal if pedestrian crossing are high. Then coming to the warrant 5. Warrant 5 is about the children crossing roads near school. So here the safety is critical. The criteria used is there is an adequate traffic graph which is less than the total crossing minutes, and it is greater than or equals to 20 children crossing during the peak period. The other measure that is to be tried firstly is the signs, flasher or the school speed zones, then the crossing guards or the grade separated crossings. So here the signals are installed only when other safety measures are insufficient. Now coming to the warrant 6. So warrant 6 mainly focuses on the coordination along the corridors to let vehicle platoon pass without stopping. Here vehicle must move in platoons. If signal spacing is the requirement, vehicle is moving in platoon, the spacing is greater than 1000 feet, and if the coordination fails if vehicles have high variable speed. So this mainly improves the flow and reduce stop and go driving in the urban corridor. Then coming to the warrant 7, that focuses on the crash experience. It is also a safety based thing, signal justified based upon the crash history. So criteria is alternative measures are being tried and that are being failed, and to reduce the number of crashes, but the crashes still persist. So first is this criteria. Second criteria is if it is greater than or equal to 5 reported crashes at 12 months susceptible to correction by signals. So these are two criteria. Then coming to the volume consideration, if 8R volume meets 80% of condition 8 and B, condition A and B as mentioned in the warrant 1, or pedestrian volume means 80% of the pedestrian warrant that was mentioned in the warrant related to pedestrian volume. So here if the main goal of the signal is to reduce the accident. So this was warrant 7. Then warrant 8 ensures that signal organized traffic on the major routes. So here the condition are, the first is the intersection of two or more major routes, then existing or projected peak hour entering volume is greater than 1000 vehicles per hour, then projected traffic volume satisfy volume 1, warrant 1, warrant 2 or warrant 3, and applies only to the major route with at least one of the following. First is the part of principal through traffic network, then rural or suburban highway entering or traversing a city, or major route in the official urban traffic plan. So this warrant is mainly about the traffic efficiency at network organization, not just intersection volume. Now coming to the warrant 9. So warrant 9 deals with intersection near railway crossing. So here the scenario is that the intersection at distance D from the railway grade crossing is present, and the grade crossing is being controlled by stop and yield sign, and one approach leads towards the railway crossing. So here the evaluation criteria is based upon distance D between the intersection and crossing, the traffic volume present in the major and minor streets, and the lane configuration thresholds, that is 1 lane versus 2 lane. So if these thresholds are met, a signal may be warranted to improve safety and flow. So these are 9 warrants, and there is one exceptional multi-warrant cases. Also, sometimes no single warrant is being fully satisfied, but multiple warrants are partially met. So this is where the exceptional cases apply. So here the criteria is that 2 or more warrants meet 80% of the specified threshold, and it is being the high risk or unusual scenario taking place, and ensures the flexibility in decision making. So signals can be justified even if standard warrants aren't fully satisfied, provided multiple moderate conditions exist. So this allows moderate condition across several warrants to justify a signal. So this was all the warrants present on the MUTCD. Now coming to the Indian road context, that is IRC 93 1985. So in India we follow this IRC manual, which broadly is similar to the MUTCD but with the minor modification. That is warrant 1 includes that minimum vehicle volume for 8R is just like the MUTCD in warrant 1. Then warrant 2 is interruption to continuous traffic, that is similar to MUTCD warrant 1 condition B. The third warrant is the minimum pedestrian volume, just similar to the MUTCD warrant 4. And warrant 4 is accident experience, like similar to present in MUTCD warrant 7. So here we have the exceptional cases. If 2 or more warrants meet 80% of the threshold, signal may still be justified. So these are the warrants that is been used in the Indian roads, that that is similar with some of the similar to some of the warrants present in the international standards. So this is a comparison table where in MUTCD we have the different warrants for 8 hour, 4 hour, peak hour. Then for pedestrian volume we have for 4 hour and peak hour. Crashes experience if there is greater than 5 crashes. Then we have school crossing warrant, coordinated signal warrant, grade crossing warrant, and exceptional 80% cases. For IRC 93 we have 8 hour in the warrant 1, and then interruption to continuous traffic in warrant 2. Then we have pedestrian in warrant 3 and accident experience in warrant 4. Whereas these are been not included in IRC 93, whereas the exceptional cases has been also allowed in the IRC 93 1985. So this is all about the warrants that has been used to justify the traffic signal control. So summarizing this, so signal justified for the safety, efficiency and network management. MUTCD has additional warrants for school zone, coordinated signals and near rail grade crossing, whereas IRC mirrors MUTCD but it is less comprehensive, and there's still upgrade is been going on. So decision is being hierarchical. Firstly is to satisfy the primary warrants, then check for the exceptional multi-warrant 80% rule, and also consider the network and special conditions such as isolated communities, speed adjustment, or the number of lanes that has been present on the major and minor streets. So before moving ahead, is it clear? Is anybody having doubt up till here?
No, ma'am.
Okay. Okay, so now moving ahead with the basic signal terminologies. So we have different terms that has been used in the traffic signal. So first one is the cycle, then is the cycle length, then the phase, then interval. So now going through them one by one. So cycle, so one complete sequence of signal indication that includes red, green, then amber, and then again red. It completes the one cycle. Then comes to the cycle length. Now cycle length means the total time required to complete the full one cycle is the cycle length. Then next we have is the phase. So a phase is a portion of the cycle that has been allocated to a particular movement or combination of non-conflicting movement. For example, north-south traffic in one phase, or east-west traffic in the other phase. Finally, there is an interval, then time, it is known as the time duration, that is during which the signal indicates does not change. We say the green interval or the red interval time. So the overall objective of signal control is to separate conflicting traffic movements in time. Now, different types of the signal controls. So there are mainly classified into two categories. One is pre-timed or fixed control, and the second one is actuated control. So in pre-timed control, everything is been fixed. The cycle length is fixed, the phase sequence is fixed, the green time distribution is also fixed. So signal operates in a repetitive order. So these timings are mainly designed using the historical data, using collected data from the peak hours. Sometimes different timing plans are also prepared for the, we fix different times for morning and evening peak duration, whereas different for the non-peak durations. But the main limitation is that this system cannot adjust to real-time traffic variations. If traffic varies unexpectedly, the signal timing does not adapt. Therefore, other times we sometimes we use the actuated signal control, that is the second type of signal controllers. So in actuated signals, we adjust their timing based upon the actual traffic demand. They use detectors or sensors that has been installed on the roadway approaches to detect vehicle present, and on the basis of the volume of the traffic we decide the cycle length of the signal. So here the green time is not fixed, even the cycle, sometimes cycle duration is not fixed, and it all depends upon what is the traffic volume in particular approach. If one approach is having more traffic as compared to the other approach, so we give more green time to the first approach as compared to the second approach. So there are three types of actuated control. First is fully actuated. Here where the detectors are installed and on all approaches, and all phase are demand based. Here all phase has been depending upon the what is the traffic in the real time. Then comes the semi actuated. Here where detectors are installed only on the minor approaches, whereas the major road gets default green time. This is semi actuated. Whereas the coordinated actuated, so here the coordination is being done along a corridor. So so to maintain this coordination, there has been fixed cycle length that has been done, but minor movements are still based upon the detection. So whatever is the signal cycle length in a particular corridor, all the intersection will have same cycle length in the coordinated actuated control signals. So these are the three types of actuated control. First one is all been where all phases and all cycle length is being dependent upon the traffic, whereas in semi-actuated only detectors are only present on the minor approaches, whereas the major road gets default gain. And third is coordinated, where the cycle length has been maintained depending upon the cycle length of the whole corridor. So now coming to the operational modes of turning movements. So here there are three types of turning operations. First one is the permitted movement. In this case, turning vehicle must yield to the conflicting vehicle or pedestrian. Its efficiency depends upon the gap availability. The second is the protected movement. Here turning vehicles are given an exclusive phase with no conflictive movement allowed. This improves the safety. The third is protected permitted movement. This is combination. During one part of the cycle, the turn is protected. During another part, it is permitted along with the through traffic. So so here for example, if we take the intersection and we allow the left turning vehicles, but here the signal turns green and the vehicles are also coming straight. So the vehicle present in this the turn left depending upon what is the gap present on the road. Whereas this is the first type, there is permitted movement. Then is the protected movement, where no conflicting movements are allowed. Exclusive phase is being given for the left movement or for the straight. Then third one is for the first phase, for example, for first phase only the straight movement is allowed, whereas in the second part of the cycle the both of the movement is being allowed. So this is the combination of both the modes. So these are the different operational modes of turning movements. And then coming to the signal phase and ring diagram. So a phase diagram shows all movements allowed during the phase in one block presentation. For example, in one block presentation we determine whether if a signal turns green, then vehicles coming from this direction will move in all the direction or just the right and straight. So this phase diagram shows the movement during a phase in one block diagram, whereas a ring diagram shows different movements are controlled within the control structure. So modern controller use dual ring structure. So this allows concurrent green signals for non-conflicting movement. What does that mean? That means if we allow together this plus this movement, and in whereas if there is the divider present on the road, so then we apply the right plus straight for this. So here the concrete green for non-conflicting movement is being allowed. This provides flexibility in phase duration, more efficient than single ring systems. Now coming to the movement groups. So a movement group consists of traffic movements that are served together in one single phase. So whatever the group is being allowed to move in one particular single phase is known as the movement group. So here this right turn plus straight and this right turn plus straight comes in the one movement group if we allow these movement to take in one single phase. Then if turning movement has an exclusive lane, it forms its own movement. If lanes are shared, the movements from the shared lane are grouped together. Then the important thing is to understand is that movement grouping depends upon how the signal phase is designed, that is which movement receive right of way together. So whatever movement of the vehicles are being allowed together in one phase comes as the movement groups, whereas the lane groups is based upon the physical lane configuration, not the single signal phase. So this includes the exclusive turn lanes that are designated as separate lane groups. Shared lanes are also treated as the separate lane groups. Sometimes movement groups and lane groups may be the same, but in some cases they are different. So remember that the movement group is based upon the signal operations, whereas the lane group is based upon the physical lane layout. So this is about the movement group, then lane group. Then coming to the critical lane group and critical volume. So within each phase, one lane group will carry the highest traffic volume. That lane group is called critical lane group. So for example, there are multiple lane groups and one of the lane will have more traffic volume as compared to the other. So the So that lane which has the highest traffic volume is termed as the critical lane group. Then coming to the traffic volume, that the traffic volume associated with that critical lane is termed as the critical volume. So this critical volume determines how much green time is required for that phase. So if there is two lane, one lane will have for example has more vehicles as compared to the other lane. So this lane vehicles are termed as the critical lane group, and the number of traffic volume present on this lane is termed as the critical volume. So this critical volume determines how much green time is required for that particular phase. So when designing a signal timing, we just focus on the critical lane group, because if we can serve this group adequately, then the other lane group is in this same phase can also be served. So whenever we design a single timing or single intersection or capacity analysis of the signal, then we mainly focus on this critical lane group and its volume. Okay, now coming to the vehicle flow at signalized intersection. So here flow starts at 0 during red. After green, discharge increases. Gradually it reaches to the saturation flow, that is the maximum flow. So then from green when it turns to yellow, then again to red, then flow decreases, but not instantaneous due to driver behavior. Then all red interval occurs when all the legs of the intersection has red signal. This ensures that the last vehicle clears intersection before conflicting movement begins. Now the key terms are the saturation flow. Saturation flow is the maximum discharge. If green is always available, then startup loss time is the initial vehicle that takes a time to accelerate, that is the startup loss time. So if in the intersection, as the traffic light turns red, there is some loss of the time, that is in second, that takes place before that initial vehicle start moving. The reaction time that takes place before the first vehicle start to cross the intersection, that is termed as the startup lost time. Then end lost time, it is the delay at end of green until intersection clears. So this is the end of lost time. Now we will see in deep what these key terms means and how are they been calculated one by one. So first is the saturation and saturation headway and saturation flow. So the first headway, the time of first vehicle to cross the stop line is the first headway, whereas saturation headway is a constant headway after initial vehicle that corresponds to the maximum discharge. So first vehicle, as I mentioned, the first vehicle takes a bit longer to cross, so that is termed as a first headway. But as more vehicles follow, the headway decreases and eventually stabilizes to a constant value. That constant headway is termed as the saturation headway, and then saturation flow rate is been calculated as using the formula as the 3600 divided by H. So here the H is the saturation headway. Then this represents the capacity of an approach lane or the lane group if continuous green has been present. So it is important for calculating effective green and the lane capacity. So we can think as if it has a lane maximum capacity if signal never turns red. So this concept is crucial when we later calculate effective green and lane capacity. So here at that moment we will need this saturation flow rate. And then comes the lost time. So traffic isn't perfect, so we account for different lost times. So first is the startup lost time. So startup lost time is defined as an extra time for first few vehicles above the saturation headway. Then comes the end lost time, vehicle that during yellow or all red vehicle aren't moving at full saturation flow. So that is termed as the and lost time. So this if we explain, so initial vehicles takes more time to cross the stop line. So if we ignore that, then the all the vehicles that are present in this intersection will move at a constant headway, that is saturation headway. But there will be a movement at the end when the vehicles are crossing during the yellow or all red period. At that moment the vehicle will not flow at full saturation flow. They will have more headway. So that the loss that takes place at that moment, because though more number of vehicles can traverse the intersection, but as vehicles are not present, so that is termed as the end lost time. So total loss, or some vehicle don't they are in dilemma whether to cross or not cross, so that has been termed as the end lost time. So the total loss time is equals to L1, which is equals to L, which is L1 plus L2, and the effective green, also been termed as GE, is the actual duration during which traffic flows at saturation rate. So effective green can be calculated as the total green time when it is green plus the time when it is been yellow or amber plus all red time minus the L, the total lost time. So this identifies as the effective green time during which the traffic flow at the saturation rate. So vehicle move firstly at green portion when the traffic light is green. Vehicle also move when the traffic light is amber or yellow, and vehicle also moves or clears the intersection when it is all red in the all legs of intersection. But there is the loss that is happens because the vehicle are not traveling at full saturation rate, that is being subtracted using the total loss time. So this determines this effective green is what really determines the intersection or the lane capacity, not just the nominal green light. So now coming to the yellow change or amber change interval. So this is the duration. The signal shows the amber light before red. So mainly its purpose is to allow the driver firstly to either to stop safely before stop line or proceed the intersection safely without speeding. So it avoids the dilemma zone area where vehicles cannot stop safely or not proceed without the acceleration. So if yellow light is too short, some vehicle may end up in the dilemma zone, a place where they can't stop safely but also can't clear the intersection without accelerating. So the yellow light interval mainly depends upon these three. It has been decided depending upon these factors. First is the approach speed, that is 85th percentile of the speed. Then the reaction time of the driver, then the deceleration, and the grade of the road. So ITE suggests a formula to calculate the yellow change interval time, that has been calculated using the formula t plus 0.28 into v of 85, the speed of 85th percentile speed, divided by 2a plus 19.6 g, where the t is the perception time, reaction time, v85 is the 85 percentile speed, a is the acceleration or deceleration to stop the vehicle or to proceed or cross the intersection, and then is the g is the grade of the road. So this is the formula that can be used to calculate the yellow time interval, yellow light interval. So this ensures that the vehicles are either that vehicle avoids that dilemma zone and are either stopped before the stop line or have crossed the intersection safely. Then comes the red clearance interval. So the red clearance intervals comes next. That is really important to make sure that the last vehicle that is entering during the yellow clears the intersection safely before conflicting traffic gets green. So the formula that is being used to calculate red light is W plus L divided by 0.28 into V of 85 minus TS, where W is the intersection width, whereas L is the vehicle length, T is the startup delay of conflicting movement. So mainly this is the interval. So the red time has been taken as the summation of distance of this, the intersection width, plus the vehicle length, because we need to stop the vehicle before the stop line. Okay, so this is it can be either this way around or the other way around, where the vehicle, where it is the length of the intersection plus the vehicle length which has safely crossed this intersection. So it can be the two-way around. So therefore it has been taken as W plus L divided by 0.28 into VA minus the time that has been taken as this startup delay of conflicting movement. So this ensures that the movement starts safely after all red. This is the all red clearance interval time. Now coming to the lane capacity and intersection performance. So how do we calculate this lane capacity? So it is based upon the saturation flow and the proportion of the cycle when the signal is green. So because vehicles are only traversing when the signal is green, so we are taking only that portion of the proportion of the cycle. So that has been calculated as time when it is green divided by C, that is cycle length, so that is proportion of the time when it is green, into the saturation flow rate. So this calculates the total capacity. And we have as you can see, we have taken not the pure green light, but we have taken effective green time. So it capacity is reduced by the lost times. So also how vehicles arrive at the intersection matters. If vehicle is arriving during green, delay may be lower. If arrive during red, then delay is higher. We also use quantify using a term that is platoon ratio, that is calculated using the formula P upon G by C, the proportion of vehicles arriving during green divided by that the proportion of the green time over the cycle length. So higher RP means better signal progression. So finally, I discuss the arrival types, which describes how vehicles arrive relative to the signal and how well traffic flows. So the arrival, there are different levels or type of arrival. If RP is around 0.3, we say vehicle arrival pattern like is greater than 80% at the start of the run, and the progression is very poor. If the vehicle type the RP is 0.667 for mainly vehicle arrive at for 40 to 80% of vehicle arrive during the red, which is also unfavorable. Where one, when the RP equals to 1, which means the number of percentage of vehicle that arrive is less than 40 and it is random, we say it as a random arrival. If the platoon ratio is 1.33, we say like vehicles are percentage of vehicle that arrive during green is 40 to 80%, that is favorable because then the delay will be less. If the platoon capacity is around 1.667, then majority of the vehicle arrive at during the signal when it is green, that is highly favorable. And when the platoon ratio is around 2, then most vehicles arrive at green, that is the exceptional cases. So knowing what is the arrival type and platoon ratio, that helps us to predict the delay and also optimize the green splits for better coordination along a corridor. So this is essential for signal design and traffic efficiency. So this was all about the summary for week 6 lectures. Before moving ahead, is anybody having doubt for regarding the summary of week 6 lecture? Okay, then we can begin with some of the practice questions. So this is first question, that is, which of the following statements are true with respect to manual on uniform traffic control devices warrant 4? First statement is, principal reasons for installing signal under this warrant is due to pedestrian experiencing excessive delay in crossing major street. A second statement is, a signal would be installed under this warrant if even if there is another signal with 300th of the allocation. Then C is, both 4-hour pedestrian warrant and peak hour pedestrian warrant criteria must be met. Third is, either 4-hour pedestrian warrant or peak hour pedestrian warrant criteria must be met. So which of the following statements are true? Okay, so uh, now let's discuss the solution. So let's first see what was warrant 4 about. So warrant 4 was about the pedestrian volume. So the time period that it includes was 4 hours and the peak hour pedestrian volume. Uh, then we compare the pedestrian demand versus the major street volume traffic. Then threshold was given to the speed and isolated volume. So and the question is, the principal reason for installing signal under this warrant is due to pedestrian experience excessive delay in crossing major street. So this is correct statement. Then signal would be installed under this warrant if there is another signal with 300 feet at location. That is not mentioned in this warrant, so it is not true. Then both of the 4-hour pedestrian warrant and peak hour pedestrian warrant criteria must be met. This is also wrong, because if either of the two warrant meets the criteria, then it justifies the signal. Therefore this is correct statement. A and D is correct statements and B and C are incorrect statements. Now coming to the next question, that is, with respect to MUTCD warrants, match the warrants given in the volume X with its corresponding principal reason given in volume column Y. So therefore select the correct options out of A, B, C and D. So warrant first has warrant 8, warrant 1, warrant 5 and warrant 6, whereas column 5 has large volume intersection traffic, maintain proper platoon of vehicles, encourage concentration and organization of traffic flow, and advocacy of gaps in traffic stream for school children crossing the major street. I would request you to answer the question in the chat box. Which of the following options is correct regarding the warrants? Okay, so now let's discuss the solution. So first is warrant 1. Let's go depending on the volume. So warrant 1 was about the volume, 8-hour volume or traffic volume. So warrant 1 is related to A. Now coming to the warrant 8. So warrant 8 was mainly related to traffic network or the coordination. So that is comes to C. Then fifth was regarding the school, and sixth was regarding the platooning, maintain proper platooning of vehicles. So this comes the warrant 6. So correct option out of all is C. Okay. Now coming to the next question, that is, with respect to signal control operation, which of the following statements are true? First is, in semi actuated operation, all phases are operated as actuated. Second statement is, pre-timed operation is suitable for isolated intersection. And C statement is, in fully actuated operation, detection is provided for all approaches. And D statement is, in semi-actuated operation, the controller is programmed to dwell with the actuated phase, that is minor movements. Okay, so now let's go with statement one by one. So first statement is, in semi-actuated operation, all phases are operated as actuated. That is wrong. It says that semi-actuated, it means it is not, all phases are not operated as actuated. So this statement is false. The second statement is, pre-timed operation is suitable for isolated intersection. That is true, since the pre-timed operation means that signal timing or signal length is fixed. Therefore, that is suitable for isolated intersection. Then in fully actuated operation, detection is provided on all approaches. That is also correct statement. In fully actuated, all the approaches is being actuated, therefore is based upon the real world traffic volume, where therefore it is depends upon the all approaches. Then statement D is, in semi-actuated operation, the controller is programmed to dwell with the actuated phase, that is minor movements. So here a term is mentioned as dwell. So the minor or actuated phase, that in the semi-actuated operation, do not dwell. They are only served only when vehicle call is present. That means if the term dwell usually refers to holding green like unnecessary, which isn't how semi-actuated control is operated. In this, wherever a minor phase has vehicle, that then only we turn the minor signal to green, else it is the it has been given to the major street. or it has been fixed to the major seat. Therefore, this statement is also incorrect. Therefore, statement D is incorrect and statement A is incorrect. The correct statement is B and C. Now coming to the next question. That is, which of the following statements are true with respect to change interval or clearance interval? First statement is change interval warns drivers of an impending change in the right of way assignment. Inaccurate clearance interval may lead to the criteria of dilemma zone. Or Institute of Transportation Engineers recommends a minimum value of change interval as 1. Clearance interval provides additional time for vehicle legally entered in the intersection to clear. So which of the following statements are true with respect to change interval or clearance interval? So here the word statement is written as change interval. So change interval can also be the change interval is also can be termed as the amber or yellow light, whereas clearance interval is the all red interval where we allow all the vehicles to move. Now let's discuss the solution. So first statement is a change interval warns driver of impending change in the right of way assignment. That is true. The change interval or the yellow light is specifically meant to warn the drivers that green is ending. That is, green also termed as right of way is the ending. So that statement is correct. Second is inaccurate clearance interval may lead to creation of dilemma zone. So that is, the statement is wrong because dilemma zone is primarily affected by yellow or change interval, not the clearance interval. So this statement is wrong. Then the ITE recommends minimum value of change interval as 1. That is false because ITE gives the formula to calculate the change interval. It does not gives the minimum and whereas it also says that minimum interval is typically taken as 3 seconds, not the 1 second. This statement is also wrong. Then C is clearance interval or the red interval already provides additional time for vehicle legally entered in the intersection to clear. That is correct. This is exactly for vehicles already intersection to clear safely before the conjunctive movement starts. So this statement is also correct. So A and D are correct statements. Okay. Now coming to the next question. That is, for an approach of a signalized intersection, the proportion of vehicles arriving during green is 0.67. The green time is 30 seconds and the cycle length is 60 seconds. So the question, this is the data. Now the first question is the platoon ratio for the approach is we have to calculate the platoon ratio, and then based upon the platoon ratio we have to decide what is the arrival type of the vehicle. Let's calculate the flat tone ratio. So what was the formula for flat tone ratio? So flat tone ratio RP was equals to the proportion of vehicles, yep, the RP was equals to proportion of the vehicles during green divided by the G by C. So the proportion of vehicle is 0.67 divided by 30 by 60. So the flat tone ratio comes out to be 1.34. Yeah, it comes to be 1.34. Now we have looked into a table which says what depending upon the flat tone ratio we define the vehicle arrival time. So let's go to that slide. So see, so we got the RP value as 1.34, which is closest to 1.33. So the arrival type is 4. Therefore the answer to the second question is C, that is vehicle arrival type is 4. Now let's come to the next question. So next question has mentioned its data. So firstly, considering the eastbound traffic and the traffic that moves eastward, okay. So at interact is given in the figure above with the following known characteristics. Average length of vehicle is 6 meter, deceleration is 3 meter per second square, perception reaction time is given as 1 second, entry delay is being given as 1 second, then the cycle length is given as 60 seconds, green time is given as 20 seconds, and the saturation headway is given as 2.5 seconds per vehicle. Startup loss time L1 is 2, clearance loss time L2 is 1. So this is the whole data, and V85 for NB and SB approach is 50, whereas for EB and WB is 45. Grade is 0 for southbound and northbound, whereas grade is plus 2.5 for eastbound and westbound. So first this is the data, then comes the series of questions. So the first two questions is the value of yellow change interval we have to calculate for northbound approach, and then we have to calculate the total yellow change plus the clearance interval, that is y plus r in seconds for northbound approach. So first these are the two questions, and then we have series of few more questions using the data given here. This is for the data, and the first two questions are determine the value of yellow change interval and the total yellow change plus clearance interval. What now? Northbound approach. Okay. So now, see, first was to calculate the yellow interval for northbound approach. So formula that we use is Tp plus V by 2A. So y is equals to 1. That is it is already been given. So 1 plus of okay. So first, what is this V? So V comes from the formula where it was mentioned that for the NB and SB approaches, the speed was given as 50 km per hour. So we have converted that 50 km per hour speed into meter per second. So we get 13.89 meter per second. So using this formula, further we get the putting in the equation, we get the yellow interval as 3.3 seconds. And then then we have to calculate the total yellow plus clearance for northbound approach. So here y plus r is equals to 3.3 plus L2 was given as 1. So keeping that adding with the yellow, we get the total yellow plus clearance for northbound as 4.3 seconds. Okay, now the next question was to calculate the effective green in seconds for eastbound approach, then calculate the capacity for eastbound approach, and then finally if eastbound approach has demand flow rate of 350 vehicle per hour, what is the uniform delay expected under these conditions. So these are the next 3 questions that we have to calculate based upon the previous data. That was this. You have to calculate effective green, then capacity. This is the previous one was for the northbound. Now it is for the eastbound. Okay, so what was the formula for effective green? It was G plus Y plus A all red minus the total loss. Okay, so here this Y that is the yellow time, but this one is for the eastbound. So we have previously calculated for the northbound. We have to calculate for the eastbound thing, and then we have to just put in this equation. Then we have to calculate the capacity. That is using the formula S by H. H we have it as 2.5. S is equal to 3600 divided by H. Using that formula we can calculate the saturation flow, and then we can use that to calculate the capacity. Then depending upon the putting demand flow rate as this, what is the uniform period of the questions. So now firstly as we need to calculate the yellow interval for eastbound approach, first we will calculate the speed in the eastbound. That was given as 45 km per hour into meter per second. So that will be equals to 12.5 meter per second. Then we will put in the equation to get the y. Y is equals to 1 plus the speed into 2 into a, that is acceleration, that is 3. So by putting in this equation we finally get 1 plus 2.083, that is comes around to be 3.1 seconds. So yellow interval for EB is 3.1 seconds. So after that, to calculate the effective green, we put in this equation where G effective green is equal to G plus Y plus AR minus total lost time. So G is given as 20 seconds, Y we have calculated as 3.5. The all red time L2 is given as 1 second, whereas total time is equals to 2 plus 1 entry delay plus 2, that is equals to 3 seconds. So by putting in this equation, we get G is equals to 20 plus 3.1 plus 1 minus 3, that is equals to 21.1 second. Next, we have to calculate the capacity of eastbound approach. So, saturation flow is calculated by S is equals to 3600 divided by H. So, is equals to 3600 divided by H, that is given in the question, that is 2.5. We get 1440 vehicle per hour. And then finally calculating the capacity, where C is equals to S into effective green divided by capital C. This C is the cycle length. Okay. So 1400 into 21.1 seconds divided by 60 comes out to be 506 vehicle per hour. So this is the capacity of eastbound approach. Now the next question was to calculate the uniform delay if the volume is equals to 350 vehicle per hour. So putting in the formula, this is the formula for uniform delay, where it is 0.5 into C 1 minus GE by C whole square minus 1 minus V by C into G by C. So putting these terms, we get GE by C is equals to 21.1 divided by 60, whereas V by capital C is 350 vehicle divided by total capacity that we have calculated as 506. And we have put the values in the numerator, all the values, and then we finally get the delay as 16.7 seconds per vehicle. So this is the solution. Of this. Okay, so that's all for today. Is there any doubt? Please let me know. You can mention your doubts in the chat box, or we can discuss it right now. Okay, so if there is no doubt, we will end the session. Okay, so now we are ending this problem solving session, and we will meet again in the next week's session. Thank you everyone for joining in.